For some applications, data naturally comes in vector or matrix form. For example, a vector of digitized samples representing an audio waveform over time, or a matrix of pixel colors in a 2D image from a camera. When processing that data, it's common to perform the same sequence of operations on each data element. The example code shown here is computing a vector sum, where each component of one vector is added to the corresponding component of another vector. By replicating the data path portion of our CPU, we can design special-purpose vector processors capable of performing the same operation on many data elements in parallel. Here we see that the register file and ALU have been replicated, and the control signals from the decoding of the current instructions are shared by all the data paths. Data is fetched in big blocks, very much like fetching a cache line, and the specified register in each data path is loaded with one of the words from the block. Similarly, each data path can contribute a word to be stored as a continuous block in main memory. In such machines, the width of the data buses to and from main memory is many words wide, so a single memory access provides data for all the data paths in parallel. Executing a single instruction on a machine with n data paths is equivalent to executing n instructions on a conventional machine with a single data path. The result achieves a lot of parallelism without the complexities of out-of-order superscalar execution. Suppose we had a vector processor with 16 data paths. Let's compare its performance on a vector sum operation to that of a conventional pipelined beta processor. Here's the beta code, carefully organized to avoid any data hazards during execution. There are 9 instructions in the loop, taking 10 cycles to execute if we count the no-op introduced into the pipeline when the B&E at the end of the loop is taken. It takes 160 cycles to sum all 16 elements, assuming no additional cycles are required due to cache misses. And here's the corresponding code for a vector processor, where we've assumed constant size 16-element vectors. Note that V registers refer to a particular location in the register file associated with each data path, while the R registers are the conventional beta registers used for address computations, etc. It would only take 4 cycles for the vector processor to complete the desired operations, a speedup of 40. This example shows the best possible speedup. The key to a good speedup is our ability to vectorize the code and take advantage of all the data paths operating in parallel. This is impossible for every application, but for tasks like audio or video encoding and decoding, and all sorts of digital signal processing, vectorization is very doable. Memory operations enjoy a similar performance improvement, since the access overhead is amortized over large blocks of data. You might wonder if it's possible to efficiently perform data-dependent operations on a vector processor. Data-dependent operations appear as conditional statements on conventional machines, where the body of the statement is executed if the condition is true. If testing and branching is under the control of the single instruction execution engine, how can we take advantage of the parallel data paths? The trick is to provide each data path with a local predicate flag. Use a vectorized compare instruction to perform all the a sub I less than b sub I comparisons in parallel, and remember the result locally in each data path's predicate flag. Then extend the vector instruction set architecture to include predicated instructions, which check the local predicate to see if they should execute or do nothing. In this example, addc.v.ifTrue only performs the addc on the local data if the local predicate flag is true. Instruction predication is also used in many non-vector architectures to avoid the execution time penalties associated with mispredicted conditional branches. They are particularly useful for simple arithmetic and Boolean operations, in other words, very short instruction sequences, that should be executed only if a condition is met. The x86 instruction set architecture includes a conditional move instruction, and in the 32-bit ARM instruction set architecture, almost all instructions can be conditionally executed. The power of vector processors comes from having one instruction initiate n parallel operations on n pairs of operands. Most modern CPUs incorporate vector extensions that operate in parallel on 8, 16, 32, or 64-bit operands, organized as blocks of 128, 256, or 512-bit data. Often all that's needed is some simple additional logic on an ALU designed to process full-width operands. The parallelism is baked into the vector program, not discovered on the fly by the instruction dispatch and execution machinery. Writing the specialized vector programs is a worthwhile investment for certain library functions which see a lot of use in processing today's information streams with their heavy use of images and AV material. Perhaps the best example of architectures with many data paths operating in parallel are the graphics processing units, GPUs, found in almost all computer graphics systems. GPU data paths are typically specialized for 32 and 64-bit floating point operations found in the algorithms needed to display in real time a 3D scene represented as billions of triangular patches as a 2D image on the computer screen. Coordinate transformation, pixel shading and anti-aliasing, texture mapping, etc. are examples of embarrassingly parallel computations where the parallelism comes from having to perform the same computation independently on millions of different data objects. Similar problems can be found in the fields of bioinformatics, big data processing, neural net emulation used in deep machine learning, and so on. Increasingly, GPUs are used in many interesting scientific and engineering calculations and not just as graphics engines. Data-level parallelism provides significant performance improvements in a variety of useful situations. So current and future instruction set architectures will almost certainly include support for vector operations.